Hello everyone, I am Alviator Khalil. I am going to present our work titled RollGuard Defending RPC Manipulation Attacks in Optimistic Rollups with Graph Machine Learning. The authors are myself and Muhammad Ashikur Rahman. Both the authors are from Florida International University. I'm going to provide a brief overview of the presentation. First, I'm going through some introductory information such as background and motivation. Then I'm going to talk about the contribution that we made through this work, followed by the attack idea that we discovered. And then we're going to talk about the technical details of the defense mechanism that we are proposing, followed by the evaluations that we did to validate the proposed defense technique. Finally, we'll conclude through the discussion section. So now I'm gonna talk about a bit of background. To start, we will talk about the scalability issue in blockchain. So blockchain does secure the monetary transaction, however they are not scalable, which hinders its utilization in mass application. So as you can see, the Visa cards that we use for daily uses like debit and credit cards, they have 4,000 transactions per second, and it can go up to 65,000. However, one of the most popular cryptocurrency, Bitcoin, has average of 7 transactions per second, which is really not comparable and it's not scalable as well. So there are two ways to scale. One is called the scaling of base layer or layer 1. The other approach is outsourcing the works to a new layer that is called the layer 2. So let's have a look what are these layers and how they differ. So the layer 1 means the modification in the base protocol of the blockchain network to improve the scalability. The approach is like let's say making a larger block or having a new consensus that is faster. The fees can vary, but normally they're more than the protocol itself. The transaction rate are better than the base protocol, however it's not like very high, it's moderate. The example are like the sharding, directed acyclical graph, alternate consensus. The layer 2 is more like involving the off-chain services or networks to improve the scalability. It's like sharing the transaction ordering and processing workload with the off-chain. The fees are generally very lower compared to the layer 1 solutions, and the speed is very fast. It is faster even than the layer 1 scalability solutions. Some of the prominent examples are payment channels, rollups, plasma, etc. So optimistic rollup is one of the most prominent layer 2 solutions that are existing right now. So let's talk about that. So optimistic rollup system is one of the prominent L2 scalability solutions. It reduces the on-chain operation and minimizes the transaction fees. The widely used optimistic rollup system are Arbitrum and Optimism. However, the optimistic rollup does suffer from the centralization concerns due to a sequencer is an entity that is responsible for ordering the transaction. So since this is a single entity, there is a centralization problem. The introduction of multiple processor or aggregators in the layer 2 rollup ecosystem addresses the centralization to reduce single point of failure problems. So in this part, I'm gonna talk about how a transaction transpires in optimistic rollup system. So as you can see, this is a more visual way of showing the layer 2 where the aggregator resides, and layer 1 where the main chain, the base layer chain resides, and also there is an ORS operator called the verifiers. They also reside in layer 1. So when a user tries to do some transaction on optimistic rollup system, he has to exchange his layer 1 token or coins with the layer 2 tokens. As I mentioned, for doing that exchange, there is a smart contract that resides in layer 1 that helps the users to do the exchange. User have two options. They can send the transaction to the mempool directly, and they can receive corresponding L2 tokens that they can send to a buffer that is called the Bedrock's mempool. So they can, let's say, change their 100 coins with, let's say, 300 tokens. Let's say that's the conversion rate, and with that 300 L2 token, he can do a multiple transaction and send the request to the mempool, or the user can directly send his L1 tokens to the smart contract, and the smart contract can do the transaction request for him. And then from that buffer Bedrock's mempool, the aggregators are assigned a set of transactions to perform the execution and validation. They does that and roll up multiple transactions together to like have a compressed version of the transaction confirmation and send it to the verifier, who decide on L1 to check or monitor the submission. They can raise a challenge if they detect any invalid or fraud transaction. If the fraud is actually proven, then the transaction will be reverted and verifier will get some reward, where the aggregator will have some bond slashed from their collateral. On the other hand, if the challenge is not valid, basically, in that case, the transaction are added to the main chain, and the verifier who initiated the wrong challenge will be penalized. Now I'm going to talk about the motivation of this work. So remote procedure call, or the RPC endpoints, serve as the primary interface for users, wallet, and application to interact with the L2 blockchain. They allow clients to send transaction, query blockchain data, and interact with smart contract. Existing ORS trust RPC URLs for transaction verification, assuming their integrity. Malicious users can modify their RPC URLs during the transaction processing, creating an inconsistencies that deceive the verifiers. And that leads to unnecessary fraud challenges, slashing honest verifier, and decrease of throughput. So RollGuard, a proactive ML approach that we are proposing in this work, it detects abnormal RPC address changes, and it mitigates that RPC manipulation exploitation. Now let's talk about the contributions that we made through this work. We identified a novel attack techniques. So we are the first to expose the RPC URL manipulation attack in Optimistic Rollup. Then we proposed the RollGuard framework, that is a graph machine learning based mechanism to detect and mitigate the identified attack. We also analyzed the security throughput trade-off and evaluated how different risk threshold and challenge rate impact the security and performance. And finally, we did experimental validation of the proposed defense and demonstrated RollGuard's effectiveness in reducing false challenges and improving verifiers' reward. So in this part, I'm gonna talk about the identify attack and how it have to be performed, or how the attacker does launch this attack. So as you can see, there are multiple users. One of them is attacker, from user 1 to user n, and they each have a RPC URL. As you can see, HTTP U1 for the attacker, it is HTTP UA, and for all the other users the same pattern. And the timeline shows the different phases of a transaction processing. So T init means T initialization time, and T request means the request of the transaction, and all of them submit the transaction to the aggregator. The aggregator receives it. It is for the validation period, and he does the validation, execution, and compress of the transaction. Also calculates the new state root of the L2 blockchain. And as you can see, the attacker doesn't do anything. He has the initial URL that he had, and everything goes as normal. As the submission is done to the verifier by the aggregator, the attacker changes his RPC URL to HTTP FRA, fraud A. Previously it was UA. So basically, at that time when it is already calculated, and during the time when it is been submitted, at that time the attacker changes it, and the verifier, they receive it, and then they will say, okay, since what we found is a URL which doesn't match with the current URL of the user, so they might challenge it, and later, after challenging, when the dispute phase is there, they will see that it is like it was a valid proof because it was the same user. It was not a different user. They just changed the address, which is perfectly fine and allowed, and by that the verifier will are deceived and they will receive the slashing penalty. I'm going to introduce the RollGuard framework in this part. So it uses graph neural network or GNNs to analyze the transaction pattern, constructs a dynamic graph where nodes represent the RPC endpoints. So each user have a RPC endpoint, so they represent the node. Models the ORS transaction as graphs with the nodes as the RPC endpoints as I mentioned and edges as the transactions. Detects the abnormal RPC address changes in real time. So GNN aggregates the transaction pattern to identify the anomalies. There is two factors, the risk threshold and challenge rate, that balance the security and the throughput. The benefit is this framework detects the suspicious activity early, reduces the false challenges and the penalties. In this part, we show visually how RollGuard performs the defense. So as usual, when the market route and the transaction batch are submitted to the verifier, they do the suspicion or non-suspicion. So if it is not suspicious, then it will be added to the main chain. However, the attack happens when it is suspicious. So there, before going to the challenge, there will be the RollGuard framework, and that will detect, okay, if this is a challenge, that might be something deceiving the verifier. So if it is like that through the historical training of RollGuard, if it is a manipulator, then that means there is no problem. It was not a wrong information, so it will be added to the main chain. However, if it is actually a genuine tampering of transactions, so the challenge was valid, then it will go to the dispute phase. In that way, there is no way the verifier is slashed when he is actually like mistakenly doing the challenge. And if that is valid proof, if indeed it was a wrong challenge from two perspectives, then he will get a slash. Otherwise, if it is not, then the batch will be discarded and verifier will be rewarded. So now we go through the evaluation that we perform. So first we want to show the impact of the RPC manipulation attack on throughput. So here we show the gas limit that detect the number of batches in a block. So the results show that linear decrease in throughput as gas limits and attack intensity increases. The attack reduces the number of rollup batches processed by up to 40%, impacting efficiency. The higher attack probability leads to greater throughput, which is shown by alpha. So the higher attack probability leads to greater throughput utilization due to increased dispute. Here we show the effect on verifiers reward and slashing. So as attack probability alpha increases, verifier reward decrease significantly due to more false challenges. The verifier face higher slashing penalties when mistakenly flagging legitimate transactions as fraudulent. At alpha is equal to 0.8, verifiers' earnings drop by over 80%, reducing incentives to participate. Attackers exploit RPC manipulation to mislead verifiers, causing unjustified economic losses. Now we show the training and inference performance of the GNN models. So we experiment with three GNN architecture, the GCN, GAT, and GraphSage, that were tested for anomaly detection performance. Training loss converges faster for GCN, but GraphSage generalizes better for detecting RPC anomalies. GraphSage outperformed the other models, achieving the highest AUC, which is 0.92 in detecting RPC manipulation. Results show that GNN-based anomaly detection significantly improves over rule-based filtering methods. Here we validate the RollGuard's effectiveness in terms of defense. So it reduces the false challenges, leading to higher verifier reward compared to the unprotected system. The framework successfully prevents unnecessary slashing, maintaining protocol integrity. Even under higher attack probability, like alpha is equal to 0.8, the RollGuard mitigates financial losses for verifiers. Experimental results confirm a major security and efficiency improvement in optimistic rollups. So here, finally, we explain with the trade-off with respect to risk threshold and challenge rate. So a lower risk threshold increases the security but results in frequent unnecessary fraud challenges. On the other hand, the higher challenge rate enhances security but slightly reduces the transaction throughput. The optimal tau is equal to 0.018 and sigma is equal to lambda is equal to 0.42 achieves a balanced trade-off between security and efficiency. So those are the values that we found from the experiment. Fine-tuning these parameters is crucial to maximize both protocol safety and network performance. To conclude, we identified a critical security vulnerability in OS stemming from RPC address manipulation. We proposed RollGuard, a novel graph ML-driven security solution leveraging GNNs to dynamically analyze blocked interaction and detect anomalous RPC address change in real time. The experimental results demonstrate that RollGuard significantly reduces false positive challenge rates, offering early detection of potential attacks and safeguarding verifier from undue penalties. In our future work, we will try to enhance the GNN's adaptability to evolving attack strategies. Finally, I would like to thank you for listening to my presentation, and I will be happy to answer any questions that you have.